Okay, so we're now up to section 5 of the syllabus. Sound is also a very important communication medium for humans and other animals. The old saying goes, if a tree falls in the forest and there is no one there to hear it, will there still be a sound? 18th century thinkers pondered over this question just as it puzzles people today. We now consider sound to be a combination of physical vibration causing movement of molecules and a physiological sensation recorded in the animal's brain. The material through which the energy of a sound wave travels is called the medium. Media may be a solid, liquid, or gas, but must contain particles that are able to be displaced or moved and then return to their original position. In 1660, Robert Boyle performed a simple first-hand investigation where he hung a watch with a good alarm from a thread into a glass jar. He then pumped the air from the jar, creating a vacuum. We silently expected the time when the alarm should begin to ring, and were satisfied that we heard the watch not at all. Wherefore, ordering some air to be let in, we did by help of attention begin to hear the alarm. Boyle had showed that sound does not travel in a vacuum. Sound requires a medium for propagation and transmission. Sound cannot be transmitted through a vacuum as there are no particles produce a wave. We can see a modernized version of Boyle's experiment in this video. Take notice of the sound of the bell as they remove the air from the jar and then when they open the valve to return the air again. As we can see, the amount of air in the jar has been reduced. As we open the valve to let more air in, we notice the ringing getting louder. So this brings us to our first dot point for this section. Which says, explain that sound is produced by vibrating objects and that the frequency of the sound is the same as the frequency of the vibration of the source of the sound. So again, here's another little video that explains what sound is, and then we'll move on and have a look at some information for the actual dot points.
So what is sound? It's produced by vibrating objects. Can you hear that? All matter is made of particles. As the ruler bends forward, it pushes particles in the air closer together. This makes a region known as compression, which moves forward like a stack of dominoes pushed over. As the ruler moves backwards, the particles in the air move further apart, making a region called rarefaction. The ruler moves forward again, making another compression, which forces the rarefaction and first compression forwards. In this way, compressions and rarefactions move out from the ruler, making a sound wave. But it's not just a noise that we hear. We can hear if the sound is low or high, low-pitched or high-pitched. The pitch of a sound is determined by the number of vibrations produced in a second. That rate, or frequency, with which sound waves are produced is very important. The higher the frequency with which the air vibrates, the higher the pitch. The lower the frequency of air vibrations, the lower the pitch. Frequencies are measured in units called hertz. We can hear with our ears sound frequencies from 20 hertz, that's 20 vibrations a second, up to 20,000 hertz.
Now let's look at how these ideas apply to music.
Sound waves on an oscilloscope look like this. It's like a graph of the sound wave. Again, for high-pitched notes, the waves are close together. For low-pitched notes, they're further apart. This is a pure C note, the type you get from a tuning fork.
Okay, so we're actually going to have a look closer at using the crow in class. So let's just have a look at some of the ideas behind sound. So sound originates when something vibrates rapidly enough to organize the movement of molecules so as to send a compression wave through the medium. The wave can only travel through a media which contains particles that can be compressed or spread apart. The particles move backwards and forwards in the same direction as the flow of energy. You should understand that it is the energy that is transferred, not the actual particles themselves. As you can see in the picture, the particles come together in areas of compression and then spread apart again as it moves from the source of the sound towards your ear in this picture here. So we can see areas of compression here, areas of refraction here, and the particles continue to move backwards and forwards. So the energy moves backwards and forwards until it reaches our ear. Waves can be measured in terms of their frequency, wavelength, and amplitude. The frequency of vibrations is the number of waves which pass a given point in 1 second. Frequency is expressed in cycles per second, and 1 cycle per second is called a hertz. Frequency determines the pitch of the sound. High frequency vibrations result in high-pitched sounds, and correspondingly, low frequency vibrations lead to low-pitched sounds. The wavelength of a sound is the distance between the centers of two adjacent compressions or refractions, or here between two crests, or we can also measure the wavelength between two troughs. Low frequency sounds have long wavelengths, while high frequency sounds have short wavelengths. The amplitude of a sound is the maximum distance that a particle moves away from its original position. It's also noticed by the height of the wave. So we can see here that a low amplitude, so a low height of the wave determines a quiet volume, and a higher amplitude determines a louder volume. So what we'll be doing is we'll be having a look at using the crow, so that little machine shown in the video that showed us the graph-like image of the different waves. So we'll actually be producing some of these waves ourselves using different types of sounds. So just like we looked at with light, we need to be able to have a look and explain why sound is a useful and versatile form of communication. So unlike light, sound is able to bend around objects and travel around corners. It travels through all substances, whether they are solids, liquids, or gases. So obviously light cannot pass through a solid. It can pass through some liquids depending on their density, and obviously light can also pass through a gas. Whatever the habitat an animal is, they are always surrounded by a sound transmitting medium, whether they're terrestrial or aquatic. An animal's reliance on sound, not only for communication, but also for the overlapping functions of navigation and hunting, is therefore always supported by its environment. Animals do not have to be in visual or direct contact to communicate. When visual, tactile, or olfactory, so smell sensors, are impaired or absent, sound can be used as the primary method of communication. A variety of sounds may be produced by varying the pitch, loudness, or tone of the sound, and different things can be communicated by obviously a louder volume, usually means more urgency, higher pitched can sometimes refer to pain, so a wide range of things can be communicated in a short period of time. Sound, particularly low-frequency sounds, will travel much longer distances. Toothed whales use sound in a similar way to bats. They emit sounds and then listen for the echo to come back to them. This type of sonar, which refers to sound navigation ranging, works well even in complete darkness. It is referred to as echolocation. By this process, killer whales are able to judge distance, direction, size, shape, and speed of objects in the water. So we'll be having a look at echolocation in bats, so the use of high-frequency waves a little bit later. But at the moment, we're going to have a quick look at how sonar works with whales to help them find food in the darkness of the ocean.